this is Mr. Coates, and this is APES lecture number 48, Depletion of the Ozone Layer. When we talked about ozone back in air pollution, we said that the ozone down here in the troposphere is a bad thing. This is considered a pollutant, and we don't want that in the atmosphere at all. We don't want to breathe that because ozone's very reactive. It'll actually destroy your lung tissues. So ozone's not a good thing there. However, ozone up here in the stratosphere is very important, and we do need this ozone. And so this is going to be where we're going to focus here, is on this good ozone. Remember that ozone down here in the troposphere is not a good thing. We do not want this, and it's considered a secondary pollutant down there. So how is ozone made in the stratosphere? Basically what happens is that we have high-powered UV radiation. It's higher powered up in the stratosphere because the ozone hasn't started filtering it yet. And this is enough energy to break apart an oxygen molecule. Remember, oxygen is O2. So there's two atoms of oxygen together in an oxygen molecule. This UV light breaks this apart, forming a single oxygen atom. Now, oxygen does not like being by itself. It's a very reactive atom. And so it will find another O2 molecule and react with that to form ozone, which is O3. And so this continues and is a natural phenomenon found in the stratosphere. Now we have to remember that the ozone layer is important because it protects us from the harmful UV rays of the sun. The sun puts out three different types of UV radiation: UVA, B, and C. And UVA and B are the most powerful and most damaging types of solar radiation. And the ozone layer thankfully protects us from these harmful rays. These harmful rays would otherwise mutate DNA. They would eventually kill all life on the planet. And without the ozone layer, there would be no life on the planet. So the ozone layer in this area filters out all these harmful UV that come in, so we don't get it down at the troposphere where we live. In the 1930s, a scientist came up with a group of chemicals he called Freons. And these groups of chemicals were very large molecules. They had lots of carbons. They had chlorines attached to them. Sometimes they had fluorines. Sometimes they had bromines to them. And he called them all by the trade name of Freons. And they were used for several different things. And they were thought to be wonder chemicals because they didn't react with anything in the troposphere. And so we could put them in air conditioning units to help with refrigerant because they wouldn't react with the metals in the air conditioning units. We could use them as fumigants because they would not react with any of the other materials that needed to be fumigated. They were also used as fire extinguishers, particularly halon systems in like restaurants or maybe hospitals where the fire needed to be put out fairly quickly. However, in the 1970s, there were starting to be some studies happening that showed a severe thinning of the ozone layer over Antarctica. And they quickly found out that the reason why the ozone layer was thinning was because of these CFCs, or these chlorinated fluorinated carbons, chlorofluorocarbons. And so what they realized is that one of these chlorofluorocarbons, or CFCs, or what they normally called freons, could destroy over 10,000 molecules of ozone in the ozone layer. And so quickly, by using these chemicals, we were destroying our ozone layer. You really need to know how this reaction works. You need to know how a CFC will actually destroy an ozone molecule. So let's go through it here real quick. So we have a CFC over here. And so we have a carbon bonded to several chlorines and a fluorine here. And there are many types of CFCs, so this is just a simplistic view of a CFC. Now the UV light comes in, and once again UV is pretty strong up there in the stratosphere, and it's enough strength to actually break off a single chlorine atom off of this molecule. Now chlorine is a halogen. It also does not like to be by itself. It likes to react with other things. Well, unfortunately, most of the other things up in the stratosphere are ozone molecules. So this chlorine will then react with an ozone molecule. When that reaction happens, an oxygen atom breaks off, forming chlorine monoxide here and oxygen molecule here, O2. Furthermore, more UV light can then break off this chlorine monoxide and create a single oxygen atom, and the chlorine atom then can go back and break up the oxygen or more ozone. And so what you get is this circle here when chlorine keeps on breaking apart ozone and oxygen molecules in the stratosphere. And this is why one CFC that might have 4 or 5 or 6 of these atoms on it can break apart so many ozone molecules. And it's very hard to stop this reaction. The only way to stop this reaction is if chlorine reacts with some other gas up in the stratosphere. So there has to be another gas that the chlorine reacts with that then becomes inert, so the chlorine can't react with ozone. And that doesn't happen a whole lot. So when we talk about the ozone hole, it's not really a true hole. It's what they call a thinning. And the thinning of the ozone hole mostly accumulates around the Antarctic. And this is because this is where the global wind patterns actually blow all those CFCs. So during the winter, the CFCs actually accumulate over the poles. And they don't react too much with ozone during the winter months. However, during the summer, which tends to be around October for the South Pole here, during October, November, these chemicals then become more reactive as the atmosphere starts to heat up. And these chemicals start breaking down the ozone, and we get this periodic seasonal thinning of the ozone layer we tend to call the ozone hole. Now, ozone is measured in what we call Dobson units. And if we look at this picture down here, this is in October 2001, and I said that October is usually when the biggest thinning area occurs. But you can see that the darkest purple down here is the thinnest part of the ozone, so there's not that many ozone molecules here, or Dobson units here, whereas later on this will kind of get smaller as time goes on and we get into the colder months in the Antarctic year. Also recognize that there are areas of fairly high ozone outside of the hole. It's just because of the swirling of the atmosphere, this ozone does not make it into this area. And also this is where all those CFCs are concentrated. So this is the ozone hole, or the thinning area, this past October. And if we look at it, it covered 22.1 million kilometers square over Antarctica. And you can see Antarctica here, the outline here. Then you have areas of really high amounts of ozone. But because of the global wind patterns, that ozone just kind of tends to circulate around the hole and doesn't fill in the hole. Later on, when the temperature starts to cool off, then this ozone will start to fill in this hole. But in the warm summer months, it does not. Now, is this getting bigger? That's one of the questions. If we look a few years back, the biggest ozone hole was at 27 or so million kilometers squared. So this is actually smaller than the largest thinning area. We hope that the ozone hole is actually getting smaller. Well, I hope that gives you an introduction to ozone and the ozone hole issue, as well as chlorinated, fluorinated carbons. If you have any questions, please bring them to class.